Thank you, Vinod, for giving me the opportunity to present here. And on behalf of everyone, let us once thank the organizers. Actually, two of them are not here. But it's not easy to organize things in India, particularly to do it on a network. One node at IIT, one node here, one node at HBS. Yeah. So, yeah, congratulations for putting it together, and thank you. Okay, so I'll talk about. Apologies to those who have heard some version of this talk before. So I hope I'll have something new for you also to hear. This is work of my student Shahrukh, who's almost ready to deposit her thesis. Essentially, it's the essence of her thesis that I'll present here. So the story begins actually with this simple question that I guess everyone has at one point of time wondered about. Let's take the classical channel coding problem. You have a discrete memoryless channel. You have a finite number of messages m which you want to send by using the channel n times. You are allowed to encode and then decode at the other end. And what you want to know is what is this probability of error? This is the probability, or what you want to know is this. What is the value of this limit? The minimum over all encoding and decoding functions f and g of the probability of error, and the limit as n goes to infinity. Now, if you look at this term, if you look at this expression here, this is an impossibly complex optimization problem over functions. You have to optimize over all functions f and g, and moreover, f appears as an argument to g in a noisy form. There is no standard tool that you can apply to this. Okay, and despite this, it happens to have a very clean answer. All you need to do is pre-compute this number c, which is a explicit function of the channel kernel, and it turns out all you need to check is if this rate is less than c or greater than c, and you know what that limit is. And how does this happen? This is obviously everyone I'm sure at some point of time has wondered why does this happen, and can one explain or understand this from an optimizer's perspective? Okay, this is what I wanted, and so I got to this through a somewhat nonlinear journey, which started from where I was first looking at problems in stochastic control, and in stochastic control, there is a central issue of what is called the information structure of the problem. Information structure is essentially what information does a controller have. The information structure is said to be classical if a controller remembers all the past, and it says to be non-classical if there is if it forgets some things in between. Okay, now within the classical information structure problem, let's say, is solved by and large, and in the non-classical information structure, there are two examples that caught my attention. One is called the Witzenhausen problem, which is unsolved today, and then there is a variant of that problem due to Bansal and Bashar, which is solved. Now, if you look at the proofs of these are two instances that are solved, but the proofs differ drastically. The first instance, you can classical information structure, you solve it using dynamic programming or writing the Bellman equation. The Bansal and Bashar problem was solved making a key use of the data processing inequality. And this lack of harmony is what made me wonder if there is a way to explain this in one perspective. And then when I was a postdoc at UIUC, what I observed was that all these non-classical problems are in fact in another space are non-convex optimization problems. This problem just happens to have a tight convex relaxation. And the classical information structure problems are in fact equivalent to linear programs. And this fact was known much before this, which it goes back many years, more than 50 years. And Professor Borkar, who's in the audience, has also worked on very general versions of this. But the point here is that essentially, if you view these problems in the right space, then tractable problems are either convex or admit convex relaxations, and the unsolved problem is unsolved because we do not know the right relaxation. Okay, and then the question became, is there a similar convex analytic understanding of the information theory problem? Okay, and in particular, this is finite alphabet infinite block length information theory. Okay, and so what I'll show in this talk is that canonical problems in information theory are admit tight LP relaxations. So they are in fact LPs in disguise in some sense. This includes in the point-to-point setting of lossy joint source channel coding, source coding with and without side information, channel coding in the multi-terminal settings, Slepian-Wolf coding, successive refinement, average channel, etc. Okay, MAC with degraded message size. And the implications of this would be that it would yield new and improved converses for these problems. That would imply the Polyanksiy Verdu converse for channel coding. It would improve on the Kostina Verdu converses for source coding, Miyake converse for Slepian-Wolf coding, etc. You also get a mechanistic way of deriving converses for any problem, whether it's point-to-point or network. You get a way to verify if an expression is a converse, and a unified optimization theoretic way of thinking about converses. This is all finite block length. Okay, so let's take a finite block length problem. You have let S, X, Y take values in some abstract finite space, and I have a loss function kappa which can in general depend on everything, and I want to minimize the expected loss over all functions f and g under the information constraint that X should be a function of only S hat should be a function of only Y. Okay, and my decision variables are f and g. And so if I take in particular kappa to be a distortion or that depends on S and S hat, then that would be like finding the least distortion. If that is the indicator that S is not equal to S hat, then I'm looking for the minimum probability of error between S and S hat over all functions f and g. So once I take these to be any finite alphabet, I don't need to really talk of a block structure. The alphabet itself could be a set of all strings of a particular length, and that gives me back the block structure. Okay, and what we want to do is get lower bounds on these problems. Now, the first thing you observe here is that actually this is probably the bad way of writing the problem. That you write this as over all functions f and g. A better way is to write this over all joint distributions that are induced on all these variables, S, X, Y, S hat. So an equivalent formulation of this problem is that you want to minimize this expectation of kappa over all Qs that decompose in this way, that are a product of Ps into Qx given S into Py given X into Qs hat given Y. This decomposition arises because Sx, Y, S hat forms a Markov chain. And the unknowns here become your kernels Qx given S and Qs hat given Y. So they are sort of a randomized choice of an encoder and decoder. Okay, so this product here is what renders the problem not convex. This fact holds regardless of what your kappa is. Now here, so the way to create a linear programming relaxation of this problem is to do the following. So what we did was, suppose you take W to stand for this product, Qx given S times Qs hat given Y. Let W stand for this product, and now what we'll do is we'll infer linear relations on W. So what we'll do is you observe that since this Qx given S when summed over X equals 1, you multiply both sides by Qs hat given Y, and that gives you that sum over X of W should be Qs hat given Y. Likewise, sum over S hat of W should be Qx given S. Notice also that this product should be greater than or equal to 0, which when you substitute for the product for W gives you this inequality. And then eventually you get all these relations between W, and then you drop this requirement that W should be this product. What you get therefore are inequalities that are true if W was equal to this product, but the converse may not be true. So what you get is then a linear programming relaxation of this problem. Effectively what happens is for each S and Y, this W is actually a coupling between Qx given S and Qs hat given Y. So what we've done is effectively relax the problem to an optimal transport problem for each Qx given S and Qs hat given Y. However, note that this interpretation holds only in the point-to-point setting. In multi-terminal settings, it gets more complicated. Geometrically, what we've done is you've taken this bilinear surface and created hyperplanes around it to approximate it using hyperplanes. Now this is related to the lift and project technique in integer programming of Loas and Schreiber, Sherali Adams relaxations, Mycomic inequalities, and so on. There are many, and it is probably this way of multiplying constraints and so on is one of the most reliable ways to get to convex hulls of sets and in integer programming. Okay, so and this or variants of it are the most reliable ways of doing it. Okay, so although it looks kind of dumb and innocuous, it actually is quite powerful. In particular, if in the case of just two variables that are non-interacting in the constraints, this in fact does get you to the convex hull. Okay, and so now what you do is write out the dual of this. The dual takes this sort of form, and you'll notice here you'll notice here that in the dual there is a kind of rate-like conflict. So there's a function, there's something that depends on the source alphabet, there's something that depends on the channel output alphabet, but it's not only the cardinality that matters. There's something that every symbol gets accounted for in a detailed sort of count. Okay. Now, if you can further simplify this dual by getting rid of this gamma A and gamma B by making sure these hold with equality, and then what you get is a simple framework for obtaining lower bound. So what we need to do is construct. Suppose you get a function, get functions lambda s and lambda c that satisfy this inequality. If they satisfy this inequality, then it follows that the cost of the dual problem is a lower bound on the optimal value of the dual problem, which is then a lower bound on the optimal value of your original problem. So your converse or a lower bound on the original problem comes from simply from any construction of lambda s and lambda c such that they satisfy this. These are functions on notice that these are functions on subspaces of the full space, on the full space of S, X, Y, Z. These are functions, lambda c is a function of S, X, and Y. We call that a channel flow. Lambda s is a function of S, S hat, and Y. We call that the source flow. As of now, we have no operational interpretation for these, but we know how to work with them. So whatever they are functions essentially, and they have to satisfy this bottleneck. You find any pair of functions like this, you get a lower bound. All right. So let's see how this works. So let's take the example for BSC. So with finite block length n, and you see that the right hand side then in this case this channel coding for a BSC. So the right hand side that you have here, this is simply a function of the Hamming distance between x and y. X and y are now strings of length n. Okay, so it's a function of only the Hamming distance between x and y. So it's tempting to try this. You put lambda c to be equal to ps into py given x, and lambda s such that take it such that this inequality holds, and that then gives you this value as a lower bound. Now this is not a very interesting lower bound simply because you can take R to be slightly greater than the capacity, and then along the diagonal that one is interested in information theory, that means you put m equal to 2 raised to nr, fix R and let n go to infinity. Along that diagonal, this goes to actually minus infinity. Okay, so this is not a very interesting bound, but you can learn from this and you can tweak this, and it turns out that you can tweak this and you can actually get to this bound. And this bound is no, it just means your construction was bad. So that was a naive converse, this one, but you can get a better converse. This is in fact gives you the strong converse. Okay, so you get a term here which is, so it's 1 plus a lot of terms, and the significant one here is 2 raised to n into 1 minus h of epsilon. So that the capacity is sitting there. M is 2 raised to nr. So if R is even slightly greater than capacity, you can choose your delta in such a way that this whole thing, everything except for the 1 goes to 0, and that gives you that. So when R is greater than the capacity, you get that probability of error should go to 1. Okay, so this is so it's a matter of choosing the flows correctly, those dual variables correctly. Okay, and now if you're wondering where all my entropy terms came from, they actually come from a first principles calculation. When you work through the tweaked construction, the tweaked construction is actually very, in hindsight it seems correct, very straightforward. Instead of putting this equal to py given x, what you need to do is chop off a bit of the tail of this. So that's basically the whole idea. And so you get something when dxy is greater than this, something when dxy is less than, and so on. Work through this. What you get are binomial sums, which then you can approximate using the volume of the Hamming ball, and that gives you your, you got your the entropy exponent. Now, the converse that I just showed is, in fact, we later realized is essentially the same as the Polyanksiy-Verdu converse. Essentially the same. I'll tell you what the main differences are. Is essentially the same as that, and it improves it also improves on the Wolfowitz converse. You can look at our NCC paper in 2007 for a similar calculation for the binary erasure channel. Okay, so now come to this. This was just a baby example. Let's do the most general problem, which is joint source channel coding with any source distribution, any channel distribution, and you have probability of excess distortion as the loss criterion. We get a linear programming based meta converse here, which if you particularize in a certain way, it gives you an expression which is actually an improvement on the Kostina Verdu converse. Then this is your Kostina Verdu converse. Here you put in your block structure and calculate the asymptotics. You will get that this is in fact right. Okay, we get a meta converse that implies. In fact, there are few things missing here which I have not said. You also get other converses which imply the hypothesis testing converse if you branch out from here in other directions. So these improvements and so this is the Kostina Verdu converses, and these are particular improvements on these. These are quite a big improvement. For lossy source coding, you get something similar. You get a meta converse. From there, you particularize it in one way. You get this hypothesis testing based converse of Kostina and Verdu, which you can particularize in two different ways, and you again get one Kostina Verdu converse, another Palzer-Timo converse. For lossless source coding, this is actually it takes a particularly simple form. That what you want to do, it turns out what you want to do in this converse is find a vector phi which is in this box between 0 and PS. PS is your source distribution. Find a vector phi which is between 0 and PS, and you want to trade off optimally the L1 norm of phi and M with the L infinity norm of phi, with the scaling for the trade-off being M. Now, in one natural way to do that is to take phi equal to PS everywhere except when PS becomes too large. So chop off the biggest part of PS. In particular, if PS concentrates somewhere, you chop that part off, and that to take phi s equal to this, then you get that you get this as the lower bound, and this is in fact one of the converses of Kostina and Verdu. For channel coding, it can be shown that the LPE is in fact exactly equal to the Polyanksiy-Verdu meta converse. So this is just an alternative form of it. Later we realized that this is in fact the same, and this came because we learned of this paper of Matthews where he's arrived at exactly RLP but through a different argument. And for channel coding he was in fact able to show that these are the same. You can get another converse where which is kind of complicated to look at initially for an arbitrary loss criterion, arbitrary distortion, not probability of excess distortion. Take any distortion function and you want to know a lower bound on the expected distortion. You get this converse, and this converse as a special case yields the following. It gives you that the LP is in fact exactly tight for any Q-ary uniform source over a Q-ary symmetric channel. So this is the matched case of a Q-ary uniform source over a Q-ary symmetric channel of block length n. And here we in fact recover that the uncoded transmission is actually optimal, and the optimal distortion is in fact epsilon here, which is the crossover probability. Now this can, so let me come to multi-terminal problems. First, the simpler version, which is, how much time do I have? 10 minutes? Yeah, okay. So multi-terminal problem, let's first take something that's multi-terminal like with the where you are considering the maximum probability of error. The maximum probability of error problem is the min-max problem. You are finding the code that which gives you the overall messages, right? So it's a min-max problem, and therefore the LP is slightly loose as compared to the earlier problems where you have an average probability of error. That gives you a little bit of gap, but nonetheless, it still gives you the converses that you want for these two problems, which is the average channel. And so you get the weak converse for the average channel and the strong converse for the compound channel. So the LP is also, despite being looser than in the average probability of error case, you in fact get the right, it is still nonetheless tight, and the proof uses a subcode based argument and a method of types. Okay, so now let's take a general network problem. So now the problem for the point-to-point setting had a bilinear term, and that bilinear term arose because there were two decision makers, as an encoder and a decoder. If you have a problem on a network, the problem is again non-convex, but it is now it is multilinear terms. It's a particularly structured polynomial optimization. But the method of constructing relaxation extends mechanistically. So you can get this relaxations for polynomial optimization using the same sort of method, and so you can get an LP relaxation, but the number of constraints grows rapidly. You have to tackle that in a systematic way. Okay, feedback complicates matters further, so I have not considered feedback in this. So let's take Slepian-Wolf coding for something that we've studied well. So this is your Slepian-Wolf coding problem. Two sources separately encoded go through this channel, which is just basically an identity map, and they have to be decoded jointly. And this is the famous converse, best known converse so far, which is the converse of Miyake and Kanaya for this problem. To write out the dual problem, it looks extremely complex, but there is hidden structure in all of this. It turns out that the problem actually has a structure of a hierarchy of has a structure where there is a hierarchy of optimizations happening. There is one decision making at the highest level, another decision making subject to what you decide at the next level, at the higher level, and so on. So there is there's some intuitive hierarchy to all of this. To make sense of this, one way is to actually use simpler point-to-point problems as sub-problems, and to understand how to relate the variables of the Slepian-Wolf problem to the variables of these problems. So you can take, for example, the problem of source coding S1 with S2 as side information, problem of source coding S2 with S1 as side information, and the problem of jointly source coding S1 and S2. Consider these three problems and then relate the dual variables of these problems to that of the Slepian-Wolf problem. And then you can synthesize, of course, this straight away gives you that any of these problems give you lower bounds on the original problem, but that's not very surprising. So instead of now doing just a convex combination of points from here, what you do is a nonlinear combination. You create a nonlinear combination of these of points from each of these, and that results in a new and improved converse on the Slepian-Wolf problem. So you can get something better than the Miyake and Kanaya converse from this. So this is the master meta converse. You particularize that gives you a slightly simpler looking meta converse, which is an improvement on the meta converse, and this got chopped out. Here there is the Miyake and Kanaya converse. Okay, so yeah. Huh? Yeah, so you can check that this actually performs quite well. Okay, so I'm actually finishing earlier. So just let me end with a bit of speculation. The state of the affairs is that we've also been able to do other problems which I did not mention here, and what we found is that we've struggled where others have also struggled. We've struggled with the MAC, for example. We've struggled with MAC is of course solved, but we've struggled to get the right regions there. We've struggled with the broadcast channel, but we've not struggled with it long enough to say that we've failed. But we may be able to get improvements on some of these problems. But the fact that, difficulties are not entirely going away and they reappear in, through the back door in different forms, makes one wonder if there is some, whether inapproximability by a linear program or through some instrument is fundamentally related to the lack of succinct descriptions for certain problems. So are these, so whether there is a, now of course, this lack of succinct descriptions has to be made formal. As of now, I think it's like whether an information theorist, mortal information theorist likes it. There's no a mortal information theorist likes it. There's no, we have not made this mathematically precise of what exactly constitutes as a good enough description. This can be made precise by talking of how many hyperplanes you are allowed to add and so on, right? So yeah, but there is this. It just makes me wonder if there is this sort of connection looming. Okay, so I'll end that. Yeah, I can. Probably I have not tried weak, because I only need weak duality. So the difference in infinite dimensional versus finite dimensional linear programming is just the conditions for strong duality, which is the exact equality between the primal and dual LP. And I don't really need that equality anywhere. I have not, yeah, so if one wants to do with Gaussians or something like that, of course you would need that. But I have not had to, it depends on the alphabet eventually. Yeah.
For example, simpler segments, there's a linear program that you can write for decoding channel codes, and you decode there's also an operational meaning to correspond to the object function there that corresponds to like. I'm just wondering if there's sort of an operational meaning here in terms of code.
Yeah, so no, so that's the thing. So this is, you have to, the challenge and get as of now, I think this does not correspond to any traditional object. At least these dual variables that I've been talking about, which are my main tools, they do not correspond to any traditional object because they are on this impossibility side. All your constructions are here. This is the achievability side, right? Whereas I'm on this side, which is so there's no, it's not easy, straightforward to get that. So in fact, Professor Mittar, who's actually not here, he and I were thinking that since he had a way of thinking of channel coding through free energy minimization, and that has a dual, there may be some connection you can exploit there to explain where these things are coming from. But yeah, so as of now, I don't have a physical or operational meaning for these things. There is an operational meaning to this, to just simply optimizing over all W's. As I said, this you can say, well, I'm allowing all couplings here instead of the particular coupling where they are a product. Yeah, so that operational meaning is there. Yeah. Yeah. Submodular optimization. Yeah. Their work is to quantify how good the Polyanksiy Verdu Converse is, and so it's particular to channel coding, and they get very good answer to that. So they show that it's that Converse is in fact is extremely good. So even for a particular end, not just asymptotically tight. So there is, in that sense, there is we are talking of the same object but with different goals. Yeah. And of course, they are specific to channel coding, whereas mine is general. Yeah. I mean, they are, whatever inequality is that just appears through the calculations. It's not like I've used one kind of inequality or another. In fact, this is where I think probably the potential lies, that because you take the problem as just a combinatorial optimization problem, you treat it that way, there's a possibility for discovering inequalities that you would not have discovered through the Shannon route. Yeah, so I don't know about this, but I think there is there is a yeah, as I said, I have not used any one thing in particular. Thank you.